Hi everyone, welcome back to my channel. We're going to be looking at covalent bonding. I have a little bit on the Lewis structures for you, multiple bonds, and then we also can do a practice together at the end. Okay, so starting by our Lewis structures. When you're thinking of the covalent bond formation, we try to find a way that we can present that. And one of the really good way that is, very understandable and kind of easy to follow is our Lewis symbols. So for example, in the formation of hydrogen gas, H2, the two hydrogen atoms are trying to share their electrons in order to achieve the two electron configuration of helium, which is the noble gas. And as you can see, every single dot is presenting your valence electron, and they try to share that, right? So now we have them paired up, which is going to be exactly what we have for helium. Another example is what we have for chlorine, right? Each chlorine atom shares the electrons to complete their valence shell, which is going to be 8 electrons. Remember, we call that the octet, right? And by achieving the noble gas configuration of argon, they're going to be a lot more stabilized, which is presenting by these dots, right? So this is what we call the Lewis symbol. So in our Lewis structures presentation, we're going to have the shared electron pairs, which is known as our bonding pairs, being shown as lines, and the unshared electrons, also known as lone pairs or non-bonding pairs, are going to be presented using dots. For example, I have the Lewis structure of hydrogen, right? As you can see, there is one bond between these two. That will be our bonding pairs, right? And for chlorine, I also have one bond, but I also have all of those, lone pairs on my chlorine valence shell. The number of covalent bonds are going to be depending on where we see the nonmetals, right? In what group on the periodic table. But this is a kind of general observation. For group 17, which is our halogens, typically we only have one bond. For group 16, which is something like oxygen, right, the oxygen family, they're going to typically form two bonds. Group 15, such as nitrogen, they are forming three bonds. And group 14, which is the carbon group, right, they are typically form four bonds to achieve an octet. Okay, now sometimes we need to have more than one pair to be shared, okay, in order to reach the octet. If I have just one pair, we call that a single covalent bond, right, or a single bond. But if I have more than one pair that I need to share in order to achieve my octet, then we're going to be looking at multiple bonds, right? So for example, if I have two electrons, right, two pairs of electrons that are shared, we call that a double bond. And that will be, presenting by two lines in our Lewis structure. For example, if you look at carbon dioxide, carbon shares two pairs of electrons with each of these two oxygen atoms. And therefore, we are forming two double bonds in order to complete the octet for both carbon and the oxygen atoms, right? Okay, cool. Okay, so the next one is going to be the triple bond, right? And that would happen when we have three pairs of electrons are shared. And a really good example, a very common example, is nitrogen gas. Each nitrogen atom has 5 valence electrons, so 3 electrons pairs are going to be shared to achieve an octet, right? So when I have this triple bond, I can understand the properties of my nitrogen gas, which is kind of understandable by looking at the Lewis structure. Nitrogen is a diatomic molecule, right, that has very low reactivity. Okay, so if it's very low in reactivity, it means that it must be a pretty stabilized molecule. So it seems that having a triple bond between the two nitrogens are making this molecule pretty stabilized, right? In terms of the distance between the two atoms, it's going to be about 110 picometer, which is a very short distance resulting from the strong triple bond that I have between the two nitrogen atoms. Okay. So a little bit expansion on the multiple bonds and how this is actually affecting the bond distance. Okay, so the average distance between bonded nitrogen atoms varies depending on the number of shared electrons that we have between the two of them. For example, if I have just one pair of electron, a single bond, it's going to be 147 picometer. If you have a double bond, right, two pairs of electrons being shared, we're going to have shorter distance, so that's 124 picometer. And if I have a triple bond, right, now we have three pairs of electrons shared, that would be 110 picometer. So as you can see, this is a kind of general rule. The bond length between the two atoms always decreases as the number of shared electrons being increased, right? So the more electrons shared, the stronger the bond is, and therefore the two atoms are getting closer to each other, right? Okay, I hope that makes sense. Okay, so here's our practice. Predict the formula of the stable binary compound, which means a compound composed of two elements formed when nitrogen reacts with fluorine, and we also try to draw its Lewis structure. Okay, so looking at your periodic table, nitrogen has 5 valence electrons. Okay, so bear with me when I'm drawing these dots. And then when you're looking at your fluorine, we have 7 valence electrons. That means there's only one of them that is unpaired, right? So fluorine needs to have just one more electron, but nitrogen needs 3 of them, and therefore I need to have 3 of my fluorine to satisfy that, right? So I'm just going to draw the dots first. I've got one pair of electron, which is my non-bonding, and then I have 3 other pairs that are being shared with my fluorine, and I have 3 of them, right? Something like this. I also need to put all of the non-bonding electrons for all 3 of these fluorine atoms, right? So just be patient with me, almost there, and there you go. So if you want to draw the Lewis structure, remember we go by, the lines. I have 3 lines, which is the 3 bonds. I'm going to have 3 fluorine atoms here, right? Don't forget that you have 1 non-bonding pair for nitrogen and 3 non-bonding pairs for your fluorine atoms, right, for each of them. That's it. This is going to be my Lewis structure for NF3. Excellent. Thank you very much for watching this video. If you like it, please give it a thumbs up. There are going to be more coming up very soon for you. Take care and bye-bye for now.